All right, let's talk an integral concept now. We've put derivatives too far into the limelight, whatever you call it, whatever. Let's talk. This idea that we're gonna cover is solids. Solids? What? No, just plural. Solids of revolution. All right. First of all, let's just guess what this means. Solids. Whenever we talk about solids, we're talking about 3D objects. So you should be excited by now. In fact, I should do it in red and blue. 3D. Like this. See? Look how 3D that is. So hip. 3D objects. And revolution, think rotate. When the Earth revolves around the sun, you're rotating. Could be either direction. All right. So let's get a clue. What do we know about rotating objects? Well, we know that if we have a full rotation, the area under it is pi r squared. For any rotation, full rotation, the area covered is pi r squared. What do we know about 3D objects? Well, you probably know this in an intuitive sense, but a 3D object is just a bunch of areas combined. So you could talk about a cylinder as just an endless amount of circles connected. I guess you could talk about more of a cone shape with that. But either way, so that's the other thing. So somehow there has to be a way to connect these ideas that you could rotate an object or an equation. Wait, what if we rotate an equation? And you can decompose something into just one shape, repeated, just changed a little bit every time. So how do we combine the two? All right, let's start simple. Let's start with square root. All right. So here is the concept we're going to get into. Let's draw a square root line. Something like this. It actually looks more like a logarithm, but whatever. You get the idea. It's just something like that. There you go. I'd say that's good enough. All right, that's a square root of x, saying that this is x and this is y. All right, so here's my idea. Every circle can be represented by its radius and its radius alone. So, and integrals are great at adding things up to infinity over a finite distance. That's kind of like their purpose in life. So, here's my idea. If you can represent every circle based on only its radius, an equation for radius perhaps, you could probably get some sort of shape by revolving square root of x. Do you kind of see what I mean? All right, so here's what we're going to do. Let's get our z-axis out. Ooh, yeah, check that out. We have another axis right here. All right, and here's what we're going to do. So this, we're going to make every point on this the radius of our circle. All right? And so technically, if this is a radius of a circle, then this shape is revolving outward, to make a circle. And you could just keep on making those like, and you have a shape getting bigger and bigger based on the radius. All right? And now you have some kind of weird dome object. But I think it's cool. And we're just talking about intuition right now. So you have some dome object that you rotated. All right, that's the inside of it, and that's the outside. Let's color the outside a little thicker. All right, so if you were to just take this out of this graphing world for a second, it looks something like this. I guess it actually opens up a little more than that. Something like this. There you go. And if you notice, that's also a parabola from this angle. So this actually solves a parabola in a sense. All right, so if this equation represents a radius at every point, let's say our radius as a change in x, then you could just plug in that equation and take the integral and it adds every single one up. So here's what I'm thinking. So if we have pi and radius as an equation based on x, and we square it, and we add up every change in x, because that changes the radius as well, then this is the volume of this weird shape we created. And all we did is we just rotated this around in a sense. We just took this kind of weird shape and we rotate around so it's in 3D now. So volume of, let's call it weird shape. There's probably a name for this, like paraboloid or something like that. Or we could just call it solid of revolution. All right, so I would literally call this a revolutionary concept. A, to make a pun, and B, to, because it literally is pretty cool, and I would say revolutionary. So volume of weird, shape, 3D object. All right, so let's try this. Try this problem. This shouldn't be too hard. So r of x represents that equation right here, square root of x. All right, so what is square root of x squared? Because that's in the pi r squared formula. Well, guess what? That is pi. We keep the pi there, and we just replace it with this thing squared. What is this thing squared? It's just x, right? And then it's dx. All right, and now we could take any bound, really. And that gives us the volume of that weird shape. Let's just say ws, because I feel lazy. Now let's label this ws, weird shape. So we have a formula here. We could take the integral. Here, let's define a bound. How much volume do you think is between 0 and, let's say there's some result? Square root of 4 turns out pretty nice. So let's say square root of 4. So from 0 to 4, what is the bound? So we're going to change the bounds here. It's going to be the integral from, let's change to red for a second, from 0 to 4 of this equation, because that's just this thing just rewritten. So we have pi x dx. All right, so let's just plug in and solve. So what's the integral? Well, you can take out the pi. It's just a constant, so we took it out. What's the integral of x? Well, we know that one. That one's easy. X squared over 2. And then we plug in two results. We plug it in at 4, then subtract, plug in at 0. Hopefully you're remembering all of this from my earlier videos on calculus. All right, so we have this. So plug in 4. 4 squared is 16. 16 divided by 2 is 8. So we have 8. 0 squared divided by 2 is 0. So we have 8 minus 0 times pi. So the area under this curve, the volume under this curve is 8 pi exactly. And I really want to actually make an example that we could test, but I think I lack the capabilities of creating this object precisely. But you could see an application of this, right? So here's an actual problem I did with this concept. All right, just introducing it. I had a glass cup, and what I did is I created an equation. Your graphing calculator just can come up with equations for things based on a set of values. So I measured the glass a few distances. It looked like this kind of cup. And I said, okay, this is about a straight line, and this is about a square root curve. I actually did use square root for my equation. So what would the square root curve look like from here? So I came up with an equation for that. Let's call it f of x. And then I create an equation for this. This would be a g of x. Well, we could just separate it as two parts of a cup and plug it into this formula in the place of r of x. And then, just from that one distance measure, those few distance measures we got, I found the volume within an ounce. So that's just me bragging now, I guess. But the concept here is still the same. You can take any object, rotate it. Now, let's not limit ourselves. We can rotate it in so many ways. Man. So we did square root. Let's try like logarithm for a second, just to have some fun. Ooh, actually, that might be really hard. Let me think. The problem here is that squared, because sometimes that can make a problem harder than it needs to be. Fine, let's talk about 1 over x. All right, here's our equation for radius, and we're going to say it's 1 over x. Now let's plot our axes. All right, that's a 1 over x. Hyperbola, I believe. And what are we going to do with this? We're going to say from 1, the area from here, to, let's say, 6. All right, let's say 1 to 6. And we're going to rotate this. All right, still around the x-axis for now. So you have some weird kind of funnel shape. Almost a funnel. See what's going on here? And yeah, it rotates one more time, and then you'd have the dotted lines on the other side of the shape. So how much, I don't know, water could fit in here, for example? Let's do some of this. So let's just remind ourselves of this interesting formula. R of x, and these are x-axis, these are y's. And technically we have a z-axis, but it doesn't really show up because we're just rotating an object. So it's this thing squared dx. All right, so what is r of x in this case? It's 1 over x. So it's the integral of pi 1 over x squared dx. All right, we're making progress here. We can factor out the pi. Oh, and wait, one more thing. 1 to 6. We can't forget that. So let's see here. So factor out the pi. Let's change colors. Just keep this interesting. 1 to 6. 1 over x squared is 1 over x squared. That's saying this is actually saying this, which is interesting because they're the exact same thing. And we know the integral of that. That's pi. And now that 1 over x squared becomes that's technically x to the -2. So you increase the power by 1. So you get x to the 1, -1 that is, over, divide by what you increase it to, so -1. So this is going to be a -1 over x. We can progress here. And we plug in 6, then plug in 1. So let's do that. So plug in 6, you get -1 over 6. Then plug in 1, and you subtract that value, and it's going to be positive because you're subtracting a negative value. 1 over 1, which is just 1. All right, 1 minus 1/6 times pi is the volume. Let's just solve it the rest of the way. If you have a whole, that is 6 over 6. 6 over 6 minus 1/6 is 5/6. So we have 5/6 pi. That is our exact area right here. And I just, if it isn't obvious enough, it really blows me away. Because it's kind of a simple concept. We're just rotating some sort of circular object and seeing what happens. But this is the exact thing. And you'd say units cubed because we're, of course, working in 3D. So if it's feet, it'd be feet cubed. Inches squared, cubed, whatever. And last one, you can also... Actually, I have an idea. What is 1 divided by x? Oops. You know what? What is 1 divided by x as x goes to infinity? Let's say x goes to infinity. This is my shorthand notation for a limit, I guess. Well, it's 0. And look here. This thing, you could make the top bound infinity, and it would just go 0, because that's what's happening here. You're just dividing a piece into smaller and smaller bits. All right, so let's see here. What if we made the bounds here 1 to infinity? See that here? We're taking the whole volume of this curve here. And it's actually going to look like some kind of really interesting cone. So we have a circle on the bottom, and it converges at the top. All right? And rotate here. This is a really interesting object. Of course, it goes to infinity. It's infinitely long. But I have a feeling the area would be... Sorry, I don't know how to shade this in completely properly. You get the idea, though. It's this endless shape that I think will have a finite volume. So 1 to infinity. This is actually called an improper integral because it has an infinity in it, but we're going to do it anyway because you can. So you have pi, then you have this thing squared, 1 divided by x squared, which is 1 divided by x squared. And we're taking the derivative. Well, that becomes, we know pi can be factored out. Let's write in black so it's more obvious. All right, and 1 divided by x squared becomes negative 1 over x, right? We already said that. Then we're taking it from the bounds 1, yeah, great, to infinity. All right, so what is this hypothesized area? So let's see here. You plug in infinity. 1 over infinity, it's negative 1 over infinity, and then you subtract the other result. So subtract negative 1 over 1, which is positive 1, because the negatives cancel out, and 1 divided by 1 is 1. So this guy is 0, so get rid of that. All that's multiplied by pi. Hopefully you're following what I'm saying right now. And so that's 0, so it's negative 1 over 1, so that's just positive 1 times pi. The area of this curve, man, this is actually bizarre. I actually wasn't guessing I would do this when I started this video. The complete area of this curve, 1 divided by x, rotated around from 1 to infinity, is pi. I think that's crazy cool. And of course it'd be units cubed. All right, see what we're doing here? This is incredible. And I don't know how else to put into words. All you're doing is rotating an object, except for somehow out of the blue, you can do some simple integral problems. I would call these very simple integral problems to get these crazy, awesome results. All right. In the next video, I'll try to do a little more complicated solid of revolution problems. We'll also try to rotate around the y-axis, see what that means. And thanks for watching so far.